which is architecture in the mobile space, is putting serious efforts to provide an alternative to Intel architecture in the HPC space. While the CPU architects incorporate certain features to make the processor suitable for certain types of workloads like HPC, it is the tools and the software ecosystem built around that processor that plays a big role in adoption of that architecture. This is precisely the goal of today's workshop. Phil is going to share with us the architectural details as well as the features offered by the software tools for using ARM for HPC. I hope at the end of these two-day workshop, participants will be motivated to consider ARM for their HPC requirements. I thank Ms. Apurva Verma for arranging this workshop, as well as Phil for agreeing to tune the contents of the workshop to suit our requirements. I hope the participants will benefit from this knowledge sharing exercise and thank them for taking their time off to attend this workshop. Please do not for the organizers to improve and for their future offerings. And request to all the participants to do this and turn off their videos to make sure that the experience is good for others who may have lower bandwidths. Okay, thank you very much, and over to Rupesh.
Thank you very much.
Keep your video on.
Yeah. So before we begin, let me introduce Phil formally. So Phil Ridley is based in the UK. He works in a team of applications performance engineers, which form part of ARM's overall involvement in HPC. This team consists of 2 based in the UK, 2 in France, and 3 in the US. Each member specializes in their own particular applications domain, including computational fluid dynamics, climate, oil and gas, and the physical sciences. The main aim of this team is to help people get the best out of ARM-based HPC hardware. This might include performance projections for new or unreleased hardware, applications performance tuning, tuning system parameters, or mentoring at hackathons and other events. I am very, very thankful to Phil for accepting our request to give us this guidance on ARM-based HPC. Over to you, Phil.
Well, thank you very much, Professor Rupesh, and thanks everyone for allowing me to talk over the next couple of days. I'd like to begin the talks with a brief introduction to ARM-based HPC systems. I'll start off by just giving a general overview of what we do at ARM, the ARM processors, the architectures, and then I'll talk about how the current HPC deployments are that use ARM-based processors. So that will be the first part of the talk today. And then the next talk I will cover more on the ARM HPC tools side. That's not just commercial tools, but also the open source side of tools as well, but with a HPC focus. So to begin with, I'll just set up my screen, so hopefully everyone can see that. And please do stop me if you'd like to ask a question or if you have any concerns. There's plenty of scope for discussion.
Sorry, Bill. Can someone disable the beeping sound when someone joins the meeting, because it keeps going beep, beep, beep? If someone can do that.
Sure, I'll check the settings.
Okay, thank you.
Thanks, John. Yeah, Phil, please go ahead.
Participants can also do it. There is a message in the chat window how one can do it. In edit option, preferences, participants, you can click you can click on do not allow the sound to come when a participant joins or leaves. So even participants can do that for their respective sessions. I guess that's what is written in the chat window.
Sir, I have written that message. Actually, the host only can do that. Sorry about that.
Okay, looks like it has stopped. So Phil, I think you can go ahead.
Thanks. So as Professor Rupesh mentioned when he introduced me, my name is Phil Ridley. I'm part of a small team who form part of ARM's overall involvement with HPC. What we do basically is we help users of ARM-based HPC architecture, and that can mean anything from sort of talks like this, or going to events, hackathons, or even if an individual user has an issue with an application, we can look at it. We can try to, resolve bugs or issues that might be present in tools or something. And we work with our own internal compiler teams and also the wider open source community. So we have quite a large scope of work. So we're based globally. In the UK, there is a colleague and myself. So there are 2 of us in the UK. There are also 2 colleagues based in France, and we have 4 colleagues based in the US. 3 of those 4 are based in Texas, Austin, which incidentally is where one of the main ARM global offices is, and one the colleague in the US is based in Colorado. So that's basically who I am and where I fit within ARM, but we're a very small part of ARM's overall involvement in HPC. Now I'll talk now a little bit about the background to ARM and ARM processors in general, so not just HPC, but I think this will give us all an overview of how the company how ARM got into HPC in the first place. So one thing that you may be aware of is that ARM technologies are present in over 70% of the global population. So you may be already aware that we cover almost all mobile phones. So over 95% of mobile phones have an ARM processor, running an ARM processor. And worldwide, there are 180 billion ARM-based devices. So chances are that today you've either come across or are using a device with an ARM-based CPU in it. As a company, there are currently over 6,500 employees based globally. We have offices in the Europe, Middle East and Asia, UK, Germany, France, etc. And we also cover Asia and Pacific, India, China, Japan, Taiwan, etc. So we're a global company. Sorry, I just have a problem with my slide. Okay, so yeah, to summarize, ARM technology is everywhere. I'm going to talk in a bit more about how we work with our IP design, because one thing that you may or may not be aware of is that we don't actually fabricate processors. So we design the intellectual property IP or design of the instruction set architecture. Then we license that to partners who then go on to actually fabricate the end processor. So the processors that you may use in a device have not actually been made by ARM as a company, though we have designed the architecture, the instruction set architecture. And this model, it covers industries throughout, automotive, healthcare, industrial areas, smart home technology, wearables such as your watches. Many of those have ARM-based processors running in them. And we cover technologies such as AI, Internet of Things, and 5G. And all this together has made a very good base for HPC. Because, now over the last 10 years or so, ARM has moved into the HPC market, which I'll talk more about, obviously, as we go on today. But all our previous experience with processors in these other industries and areas has helped leverage into HPC. And basically, one reason this has happened is that ARM has always been a very good partner for co-design. So we work with the end partners with our instruction set, and then they can come up with an improved design, perhaps, for the end product, because they know the users very well. Now, I'll get more kind of detail now about what ARM is, what defines an ARM device, and basically what that is all ARM devices run a common instruction set, and this is at the architecture level, and it's been designed by ARM engineers. So this the one that's current now and has been around for around 10 years, the ARM v8 architecture. It's based on a 32-bit RISC instruction set. So the instructions are stored in 32-bit registers. And this is it's kind of simplistic compared to x86 and other architectures. But it works, okay, and we have 32-bit, 31. When the ARM v8 came out 10 years ago, it's 64-bit actually, because even though the instruction set is 32-bit, it does have 64-bit registers, so it's got 31 general purpose 64-bit registers as well, and also 32 128-bit vector registers. The vector aspect is known as Neon, and that was an extension to the original ARM v8 architecture. So at the bottom, the base architecture basically is 32-bit instructions, 64-bit addresses, and 128-bit vector registers. And over the years, you can kind of see by the evolution diagram, we've generally added in each revision of the instruction set, like v8.1, 8.2, etc., we've added extra features to suit what the applications that the architectures are being used for at the time. And you can see that this has evolved quite nicely as we go to the current 8.6 and so forth. You can see that more recently we've added features for matrix multiplications. All these are handled within the architecture, so it puts less stress on the tools and the compilers. We've added support for reduced precision, arithmetic. I'll talk more about that later. And also vectorized operations, and again, these lower precision general maths operations, suitable for, you know, a lot of applications. AI is just one of those. And we've also recently, well, actually now it's around 4 years, but the scalable vector extension has been added as well, so you can get ARM v8 point something with SVE, and I'll talk more about. I'll go into a lot of that later, but it's generally. I mention that now because the SVE is very good for HPC. It's a very good extension there. Yeah, and just to say a little bit more about that while we're here. So the scalable vector extension SVE enables the partner to implement an architecture with up to vector register sizes of up to 2048 bits. This is quite a big leap from our original Neon, which was 128-bit size vector registers. I think it was mentioned at the beginning of the talk, currently the #1 supercomputer on the top 500, the Fugaku system at Riken in Japan, is running an ARM architecture, ARM v8.2a with SVE, and it has 512-bit size vector registers. So very powerful system. One other thing I'd like to point out as well while we're here is that you may notice there's an A postfix after the architectures, and the reason for that is that we release 3 incarnations of the processors, A, R, and M. So the A is the compute, R is for real time, and M is for the mobile sector. So this is why we have the A there for compute. So I've said, before about how ARM operates in terms of its intellectual property model. We don't fabricate the processors, but what we do is allow a partner to buy a license to then design, create their own architecture, or use one of ours already. So there are basically a couple of well-known licensing models, and they are the core license model and the architectural license model. Now these will become a bit more clear, I think, when you've compared to how these integrate with processors, ARM processors that you already know. And basically what the core license model does is enable the partner to take an existing instruction set architecture from the bottom and just use it with their technology. They don't have to do too much regarding the end design. Whereas at the other scale, the architecture license, that involves a lot more processor design. So it can be a lot more difficult than if the partner takes a core license model. The architectural license model, it involves a complete design of the microarchitecture, even though the underlying CPU design can have the ARM instruction set architecture. There's still a lot more architectural features that can be tweaked, whereas with the core license model there are fewer. I'll kind of illustrate that better with a diagram in the middle, but in a minute, sorry. But if you're familiar with ARM processors, I can say that currently we have, for example, the Cortex A78. That is based on a core license model, as is for the HPC and server market, the Neoverse N1 CPU. That is a core license. Whereas if you're aware of the Fugaku Hpc system that we talked about, just that is based on an architectural license. So Fujitsu there, who have designed the chip, took an architectural licensing model from us, and then actually designed the chip almost from the bottom up. So an incredible amount of work there to design the processor. But the architectural license, obviously, the manufacturer partner more freedom to add features that they would like. We can illustrate that quite nicely with a pizza, I guess. So the core license model is basically you buy a pizza base, and then it's up to the partner to add whatever toppings they like. In terms of HPC toppings, this can be like cache models in terms of how they interact. So there isn't that much that you can change, but you can still add your own ingredients, and then you end up with a very nice pizza at the end. But on the other side, if you want to take the architectural model, that basically just gives you a recipe. So then it's up to you to cook things from the bottom up, and then add your own ingredients. So there's much more work than if you'd just taken the pizza base and added your own ingredients. So that is really just a general overview of the engagement model that we have in terms of IP, and I hope it does explain some of the confusion around how ARM based at least the HPC systems are named, rather than having just an ARM processor. It's got the partner's name on it or some other name. So now on to more HPC topics. I hope that has given you a bit of background about ARM in general and the CPU model, but we'll focus now more on HPC. So basically, almost or around a couple of years ago, we announced a new line of infrastructure-led processor designs called ARM Neoverse. Now, what this is basically is a core license model that will span the next so many years, I think it's 6 or 7 years from now, that we've committed to doing a server chip. And I guess this is kind of it kind of fits in very nicely with our overall engagement model, and you'll already I will talk more in a bit about some current ARM Neoverse based processors that are available, but it's basically ARM committing to server and infrastructure processors for the next few years, which is great. Now, just as a general overview, this is what the current roadmap looks like for the next couple of years. It's shifted a bit, because you'll see that I've got now, and now has the V1 platform, which isn't available at the moment. So we're currently on the N1 platform, the Neoverse N1, and this was kind of it was based on the Cortex A72 plus a bit more performance and extra features, and it's it was based on, it's a 7 nanometer fabrication and DDR4 RAM. So, that's where we are at the moment, and I'll talk more about a couple of processors that are available on this platform. But coming shortly will hopefully be the Neoverse V1 platform CPU. Now, the N1 and the V1. So the N1 is for compute. The V1 was for scale. So basically, when we come to N2, we're going to go back to the notation, but it will become more clear as we go on. So this is what we've got for Zeus or V1, same thing. Yeah, I mean, if you see Zeus, it means V1 and vice versa as well. In terms of fabrication size, that will be based on either 7 or 5 nanometers. So, obviously with the 5 nanometer fabrication, you should get more cores per die. You'll note that it's got, I mentioned that Fugaku, the number 1 on the top 500 in Japan, the Fujitsu machine, that has 512-bit vector registers. Well, for V1, Neoverse V1, it will have 2 256-bit registers. Again, with this reduced precision support as well. So that will be coming hopefully soon, and you'll hear more about V1 then. And then over the next couple of years or so, we should be getting even more Neoverse based architectures. So you should see processors coming out from the existing partners who have produced designs on N1 and so forth. So yeah, definitely ones to watch. As well as working with partners, we also invest heavily in research projects for processors. We were involved with the Mont project. It was run, I think it was up until 6 or so years ago, and we took a lot of research from that, a lot of knowledge. We're heavily involved in that, both on the architecture and the tools side as well. And we've been linked to EU projects in the past. We're currently involved with a project called EUREXA. That's one of the existing European centres of excellence, along with a few others as well. I mean, we're also involved with application and vertical specific projects such as EasyWaste as well. And the Max Centre of Excellence, also in Europe. But there's another one that you may have heard of, the European Processor Initiative, which is running, I think, for 2 or 3 more years to design a processor. So they have a design in mind, and that will be very interesting to watch as well. And we work closely with them. The company that's involved with that, Cypearl, and also their partners as well. So we're very active on the research front. So to summarize really what I've been talking about, why would you choose ARM, and why would you choose ARM for HPC or infrastructure scientific applications? Well, as I've mentioned, the flexibility of our processor design model allows vendors to to focus their design on what really fits best for the users, the end users out there. It's not restrictive, so you can have a C processor that has good memory bandwidth, or a certain floating point arrangement that suits a particular workload or something like that. And one way we achieve this is by having either the core or architecture licensing model to choose from, and you can see by the examples here, just to remind us that the core design, you can have something like a Cortex A78 or a Neoverse N1. The architecture design, you may recall that there's a processor, ARM-based processor, Hpc, Marvell Thunder X2. I'll talk more about that in a while, but that was based on an architecture model, and so is the Fujitsu machine that I keep talking about at Riken. The processor there, the A64FX, was based on an architecture model, and a processor that you may not have heard of because it's quite new is the Ampere Ultra. That is a very powerful processor. It's available as dual socket with 80 cores per socket, and it's based on the it's based on their own design. So I guess that sums it up on the hardware side. On the software side, we have a large community effort working towards getting applications and software working on ARM-based architectures. This covers a very large ecosystem. So from the OSs, file systems, networking, your well-known tools and libraries, compilers, and all this is not just vendor driven. We're very active in the open source community, in the research community. So it is a community driven effort. And that community spans, everything from your mobile phone or device sector up to HPC. So there's a lot of work going on with ARM, both on the hardware and the software side. So for the remainder of this talk, I'll talk about the current ARM-based processors that we have, and then some of the current deployments that are based on these processors and similar. So for around the last 10 or so years, ARM has become more prevalent in HPC. Currently on the market, we have this kind of selection of processors, most of which I've already mentioned. You may have heard of the Marvell Thunder X processors. There was the Thunder X about 4 years ago, and then more recently the Thunder X2. And also from Ampere, we've had, they started off with the X Gene, and then about 3 years ago, I think it was, the EMAG came out, and more recently the Ultra. And Fujitsu, the A64FX, the processor based on ARMv8.2a with scalable vector extension, the 512-bit vector registers. Also Huawei, they make processors based on ARM, the high silicon range. Amazon have their own fabrication company, Annapurna, who I think it was about 3 years ago released the Graviton, and then around a year ago the Graviton 2 processor came out. I'll talk more about that as well. And the European Processor Initiative, which I mentioned before, research-based, they're hoping to release their processor in the next few years. They're working with SciPearl, the company who will be working with them to fabricate that design. And then there are other companies like Fitium and Qualcomm. So there's quite a wide range of partners who are producing ARM processors, and you'll see these appear in some of the deployments that I'll cover. So yeah, going back to one of those processors, the Marvell Thunder X2, I'll describe more now about the architecture itself. So it's been around now, I guess around 3 years or so. It was designed to compete with, well, one of the aims was to compete with Intel Skylake, and to do that, it had to have very good memory bandwidth capability. So one feature is that it's got 8 memory channels, and what this does is give it's a very powerful CPU from that aspect, and you can get some really good performance with Stream. So we've seen here that it's 256 gigabytes per second, or around, not quite that figure, but around that. And that competes very well with Skylake. So you've also got on the socket level, you can have these processors as dual socket, so up to 32 cores per socket, and we've got a clock speed of 2.2 gigahertz or higher. I think there's 2.5 gigahertz available, and basically, yeah, overall they're a very powerful CPU. One point to note is that they're using the ARM v8 I think it's 8.1 with neon vectors. So we have 128-bit wide vector registers with this CPU. So that's probably, what one of the disadvantages with this processor, that it doesn't have the wide vectors. But then if your HPC workload is doing a lot of memory bandwidth bound calculations, then this is a very good fit. The other thing I'd like to point out is that these CPUs can be configured as up to 4-way symmetric multi-threading. So each of these, if you have dual socket 32 cores per socket, each of those cores can be configured as 4-way SMT. So what this would do in effect is give you the 4 times 32, 256 logical threads per node, then per dual socket node. So you could have a lot of logical threads to use if you wished. But you can have them configured as just 1-way SMT, so just giving you the 64 cores. And again, for some workloads, the 1-way SMT works better than the 4-way, and the other way around. You can also have them as 2-way SMT. There's an implication with this as well, in that depending on how you have them configured for your SMTs, it affects the way that the floating point units are shared, so between threads. So what can happen is that if your workload is say heavily floating point bound, then more than likely you're better off having these configured as just 1-way SMT, so that you've got each of the the one thread sharing 2 floating point units, which gives it full capability on that front. But on the other hand, if you've got a memory bandwidth bound application that isn't doing much or isn't able to take advantage that much of the floating points, then you're probably better off having the CPU configured as a 4-way SMT, and you have to do this at boot time, by the way. But again, it's configurable, and it's a very kind of Well, it's very useful for many HPC workloads. I'll mention in a moment about a couple of systems that are based on this CPU. So just to go a bit deeper into the details of this CPU, I've mentioned most of this already. In terms of cache structure, they're very similar to the Intel, Skylake type setup with the L1 cache, 32K setup, and L2 cache sizes as well. So that's about it. Yeah. On the Thunder X2. So the next processor is the one that was designed by Fujitsu, who I've mentioned previously. That's in the Fugaku supercomputer. I mentioned before it's based on a custom Fujitsu microarchitecture. So Fujitsu have taken the architectural license from ARM to do this. 7nm fabrication. The clock on this, it's available in 3 or so different forms in terms of clock speed, but there's nothing like you get on Intel with turbo or things like that. So it's a constant clock speed, and the interesting thing is that the cores are arranged as 4 core memory groups, and what this means is that it's basically something to bear in mind when you're considering cache sharing. So there's no L3 cache here. You've got the L2 cache is shared between each of the. Sorry, it's shared within each of the core memory groups. So again, if you have a memory bandwidth bound application, you have to take this into consideration when assigning your threads to physical cores. But it's a very extremely powerful CPU, and it's available as basically FX1000 or FX700. And the FX1000 has, it's got 48, sorry, this is single socket, by the way. And the FX700 has 48 cores per socket. So you've got 12 cores within each of these core memory groups. Whereas the FX1000 has 52 cores per socket, but 4 of those cores are what's known as helper cores. So they do scheduling and OS level tasks, whereas you've still got 48 cores to run your application. But the FX1000 is available in the higher clock speed as well. So the Riken machine Fugaku is based on FX1000. So now onto a CPU based on a core license. So the Amazon AWS Graviton 2. Now, I've already said that this is fabricated by Amazon's Annapurna Labs. So it's an Amazon processor based on an ARM Neoverse N1 core license. It's a single socket processor. You can basically use these by signing up to an Amazon AWS account, and then you can choose Graviton 2 EC2 instance as either a M6G, etc. Depending on what core configuration you want. I mean, the way it works is that you can end up sharing resources with other users, or you can have the whole physical processor to yourself, depending on what you want to request from Amazon. But if you request the full node, then you get 64 cores per socket, and the socket is arranged as it's a one NUMA node. You can choose how much memory you have. It's got fairly decent bandwidth, and then you can also use the other Amazon features, the file store, the the interconnect, the EFA. So you can build yourself a very powerful cluster on Amazon with the Graviton 2 processors. So just a quick overview of the processors that I've introduced, and this diagram really gives you a comparison between what vector registers are available, number of cores per socket, possible socket configurations, and the L1, L3 setup, clock speed, memory capability.
Excuse me, sir.
Yeah.
Screen isn't printing.
Sorry, was there a question?
Oh, your screen isn't printing.
Ah, okay. Yeah, I'm sorry about that. I'll restart the screen share.
That's good. Thanks.
That's fantastic. No problem. I'm really sorry about that. So did you get the slide from AWS Graviton 2?
Yeah, it was only a few seconds we lost, but otherwise it was all good. Okay, fantastic. Thanks. So yeah, to summarize the processes that I've just been talking about, it just really gives you the specifications in terms of how they're configured. And whether they're available as single socket, dual socket configurations, and the clock speed, L1, L2, L3 sizes, and the vector register size. You'll notice that only the Fujitsu A64FX has the SVE extension, scalable vector extension, with the 512-bit size vector registers. As you noted on previous slides with the Neoverse roadmap, coming in the future will be vector registers, with 256-bit sizes, which will be based on the Neoverse V1 design. But at the moment, we're with the 128-bit Neon size registers. So for the remainder of this talk, I'll talk about some current deployments that we have based globally, which are using ARM-based HPC processors. The first of which is based in the US, the Astra system, which is at Sandia National Labs. This came out around 3 or so years ago. The machine itself is it's housed as a Hpe Apollo 70 system. So Hpe worked with Marvell, who designed the processors, who were using one of ARM's architectural licenses to do this. So the processor, as I've talked about before, was the Marvell Thunder X2, and then Hpe put these processors into their Apollo 70 line, added a good interconnect, Mellanox, InfiniBand, and good file store, and then created a supercomputer. It's appeared on the top 500 list at several places. The most recent is, number 281.
it's a decent sized system, and it's, in total, it's got over 100,000 cores, and it's running Red Hat Linux as an OS. I mean, it's just in service. It's being used as a supercomputer to do, I guess, atomistic type calculations, and it's a current deployment. In Europe, in France, more recently, also based on a similar processor, we have at France's CEA establishment, which is to do with atomic energy. We have their Bull-based system. Now, this came out from one of the research projects so the design was first thought about in the Mont Blanc project, and this is a sort of spin-off from that. And again, it's similar to the Astra system. It's just that it was sold by Bull, who housed the CPUs, the Marvell Thunder X2 as a Bull Sequana system, and it's based in France. More recently, you may have seen on the HPC news that there's going to be a deployment in Portugal, in Porto, and that's going to be based on the Fujitsu A64FX design, FX700, and it's not in service yet, but we hope that it will be in around a year. That will be a very large system, and it will have 48 cores per socket of these Fujitsu A64FX processors. It will have the Fujitsu software stack, Fujitsu Compiler, etc. And, just to remind ourselves, 512-bit vector size registers. So it will be a sizable system when it's in service.
One system that you may...
So in the UK, we have, you may have heard of it, Isambard. Now, Isambard, it's basically, Isambard itself is a supercomputer with x86 and NVIDIA based partitions, but it's actually got two ARM based partitions as well. So it's more well known for its ARM based partitions, but the Isambard platform itself is to allow users to do comparison between architectures. So you can log on and you can run your jobs on a ARM based architecture or x86 or NVIDIA and compare the results. But basically, for the Isambard ARM-based partitions, there are now two. So there was one which came about 3 years ago, which was based on the Marvell Thunder X2 processor design. That's in the system at Sandia and in France at the CEA. But the difference here with Isambard is that it was sold as a Cray XE50 system. So a Cray XE50 supercomputer with Cray's own Aries interconnect. So it's not a Mellanox InfiniBand interconnect, but Cray's own Aries interconnect design. And it's also running Cray's own variant of SUSE, which is Cray Linux environment as an OS. It has the Cray software stack. It's just like a Cray system, it's got all the Cray profiling tools with it. Now, more recently, they've upgraded Isambard to include A64FX processors. So we now have a partition with 72 of these nodes with A64FX, giving the 512-bit wide vector registers as well. So a very powerful system. But the second partition, the ARM-based partition, is now based on a Hpe Apollo 80. So instead of it being Cray XE line machine, it's a Hpe Apollo 80. So you can actually buy Hpe Apollo 80s with A64FX chips in them. And again, it's running, for that partition, it's running Red Hat as an OS. So you've got two OSs, Red Hat for the A64FX based and Cray Linux environment for the Marvell ThunderX2 based, but two ARM-based processors running as HPE or Cray systems. And finally, as I've mentioned before, we have the Fugaku supercomputer, which is based at Riken in Japan. It was in development for several years before it was made operational a while ago. It's been, in HPC news items quite a lot. It's a very powerful system. It is low energy on a per node basis, but obviously as it's a high power system, it's not traditionally low powered. And it's, there's an awful lot of scientific research being carried out on that system, across disciplines, lots of good work coming out of that. So that basically sums up current deployments. And as I mentioned before, we have links with the European Processor Initiative project in France and the EU, which is to design a new processor over the next few years. So there'll be something coming from that, based on I guess their design. So definitely one to watch there. One other thing to note is that you can add GPUs to ARM-based processors. So we have systems already being used that are using Marvell ThunderX2 CPUs with NVIDIA GPUs bolted on. And there is a lot of support in terms of tools, programming mainly from NVIDIA on that front. But there are a lot of good tools there to use. So it's perfectly possible to use a GPU on ARM, just like any CPU as a co-host. And finally, I've already covered these, but there are cloud-based resources where you can use an ARM-based processor. We've covered Amazon's AWS Graviton 2 range, and also Ampere's Ultra processor. I think that's available from Cloud Resource if you want to try that. So a lot of deployments are in current use that have ARM-based HPC processors at the heart of the system. So that concludes the first talk today. For the next talk, just out of interest, I'm going to focus on the software side, the HPC software side, be talking about tools and how we work with the wider community to help get people running their applications on ARM-based HPC. So thank you very much, and if you do have any questions, I'd be happy to answer.
Hi, Phil.
Hi.
Yeah, I have a question. So
yeah,
this is regarding the Isambard HPC system you showed. So what I wanted to know is like, what is the use cases in Isambard HPC system, because they are taking like 3 types of partitions of processor. So like, what's kind of use case they run, like, and what's the need of this kind of architecture?
Well, when Isambard 1 was kind of thought about, the idea was because you know ARM-based HPC was quite new then. The idea was just to get a system that you could house in a single Cray system, but with different underlying architectures. You know, so you had your Intel, I think it was Skylake offerings. Something from NVIDIA and this Marvell Thunder X2 ARM-based system. So that was Isambard as it was, you know, 3 years ago, or even up until I guess 6 months ago, because you know the 864FX partition has only just been added to Isambard. But in terms of what applications are run on there, it's an academic system. So Isambard has been supported by the UK research, you know, a UK research establishment, and it was from a consortium of a group of UK universities: Exeter, Bristol, Cardiff, and Bath, together with the UK Met Office, who are one of the UK weather centres. They got together with this idea and got the funding from the UK Research Institute to get Isambard, and then it was as a platform to compare these architectures. So in terms of the HPC applications, there's quite a wide range from molecular dynamics, computational fluid dynamics, you know, computational chemistry, and weather codes that are all run on there. You know, quite interestingly, more recently, I don't know if you're familiar with the VASP code. You know, the ab initio molecular dynamics, I think it is, but that seems to be run quite heavily on there, on the ARM partition anyway.
Okay, so actually, yeah, so thanks for the clarification. Actually, I thought it's some kind of combination they have taken to achieve a kind of performance and all. And sorry, I forgot to introduce myself. My name is Abhishek Pandit. I'm a data engineer from a edtech firm, and I have some prior experience in working in Cray. Like I used the Cray machine earlier, XC40. So that's what my like introduction is. And can I ask one more question if that is like allowed?
Yeah.
Like can you give some kind of a roadmap towards like going in precision programming in ARM, like some kind of open source roadmap which I can take up towards the precision programming thing?
Sorry, Abhishek. Was that towards open source programming?
Precision programming, actually. Precision programming
Precision.
on ARM. Yeah.
Okay. Do you mean things like lower precision?
Yeah, exactly. Lower precision.
Okay. Well, to summarize, I can go into more detail about this again, but you know, recently to what the ARM ISA, we added features like the half precision float, you know, B float 16 support for that. Several maths operations and LAPAC type operations have also been added to, you know, to the architecture to try to help on that area. So we are
okay.
We have added, but the I mean it's no I guess it's expected that there'll be more coming in the next few years. That's all I can say about that.
So
but you know,
so as an end user right now, can we like have something like at the AWS end or something where we can actually practice precision programming on ARM, something like that?
yeah, you could at the basic level, well, actually, the current AWS chip wouldn't have the support because I don't think it's in the architecture that they currently use.
Okay.
But in the coming year or so, it won't be long. Yeah.
Cool. Okay. Thank you, Phil.
No problem. Thanks.
Hello. Yes. I have a question.
Yeah.
You talked about SVE. When, like for example, for Hpe Apollo 80, the SVE is till 512 bit, or is it till 2048 and it is emulated over the 512 bit hardware?
No, that's a good question. It's explicitly 5112 bit. Basically, what happens is that the architecture has it uses predicate or predication as well. So it's a different. The idea is I'll go into more detail about this later, but it's vector length agnostic type programming. So the compiler will produce executable code that will be unaware of the vector size, the vector length. But the architecture will obviously have fixed vector lengths, yes. So the registers are fixed size, 512 bit.
How did you connect data?
There's one thing I should say. I need to clear something up. Sorry. For SVE, so SVE can be up to 2048 bit wide vectors, but because we're adopting this vector length agnostic style of programming, then from the software side, or so it shouldn't really matter. Because it's agnostic, because the hardware will be using predication. But when, like, for example, the A64FX does have fixed size vector registers of 512 bit. So, whether that suits your application is another matter. But in terms of programming, from the compiler side or the application side, it puts less, because it's vector length agnostic, there will be less of an emphasis on thinking about filling those vectors with your data.
Okay, thank you. And I have a question like that. In tomorrow's talk, will you be covering something on the compilation details, what compilers and what compiler options and what performances can be expected?
Well, actually, the next talk today, I'll talk about the compilers, and I can go cover the options in more detail in that talk. Yeah.
Okay, thank you.
Phil, if you don't mind, I think we might fall short on time. So would you like to present the second part first, and then we could take questions?
Yes, yeah, that'd be great. Yeah, I'll press on with the second one. I'll just get the other slide. Thanks.
Yeah, and in case you want a break of a minute or so, feel free, because you have been talking.
Okay, I'll grab a drink.
Oh, great. Sure.
Okay, so I'll press on with the next talk if that's okay with everyone. And for the next talk, again, please stop me if you have any questions. And thanks again for attending today. For this talk, I'm going to cover the software tools in more detail, and it'll be in a couple of parts really. Firstly, I'll talk about the software ecosystem that we support at ARM, the Hpc Software Ecosystem. So I'll give an overview how that software system interacts with the applications, you know, from the OS up to the end user applications like your chemistry type codes and so forth. Also, how we engage with the community to help get you know, applications working on ARM-based HPC architectures. For the remainder of the talk, I'll go into more detail about the compilers, libraries, other tools that are available for ARM-based HPC architectures. This will be both from the commercial and open source side. So there is a lot of open source work ongoing in this area. And also I'll talk about, you know, the tools like profilers and debuggers, but just in general terms. So to start off with the software ecosystem. So in terms of HPC, we do have a very large and rich software ecosystem already. And this has several components with lots of input from several areas. So we work with basically, sorry, I've just pressed the wrong switch. So yeah, we work, so on the left, we work with the silicon suppliers such as Cray, HPE, to you know, provide OSs and tools, and we also you know, work with open source developers as well, and you know, the ecosystem covers lots of areas. Sort of you know, the well-known OSs all have ARM-based variants, you know, SUSE, Red Hat, Ubuntu, containers. You know, we work with Docker, those guys, Singularity-based containers. In terms of file systems, there are the well-known systems like Lustre, BDFS, but there's also the lesser known, like AWS have their own file system, FSX, which has support for ARM. You know, the AWS Graviton 2 C6Gs, you can use AWS file store on that. And there's also, you know, support for networking, you know, like schedulers, batch schedulers. They all work on ARM architecture. So you have, I mean, basically you have you have the same choice on ARM as you would for any other HPC system. There's a very large HPC ecosystem. And just to give a general overview of what we've talked about, you know, as I said, this covers from the OS level, you know, right up to the going through the language, you know, compilers, interpreters, up to the end applications with your workload. One thing that you is really interesting as well, we work with a company who are based in the UK called the Naro, and the reason I mention this is that one aim of Linaro is that they bring together industry and the open source community to try to help get software developed and working on ARM-based architecture. This isn't just in the HPC space, by the way. This is lots of areas like in consumer markets, mobile phones, autonomous vehicles, right up to HPC. HPC is just one area where Linaro are involved, but there is a lot of work going on. And if you want, you can download the OpenHPC deployment, the current one, and you can get all these ecosystem components all ready for you to deploy on your cluster or system, all pre-built, and working. But you don't have to go that way. You can install individual components as you like. It's just that I'm illustrating what if you want something quick. One thing that you may not have heard of is a file system called Ceph, which is developed, I think, by Susie. Recently, we had a good story. There was a very good performance and cost per performance outcome from a small run using the Ampere eMag chip with Ceph on ARM. Compared with the existing method, it gave very good performance and cost. So to summarize, like where we are on the software ecosystem in general, as I said, we don't just support the commercial side. We do a lot of work with open source. So in terms of compilers, we support both the GCC and LLVM tool chains. There are a lot of colleagues at ARM who work with those tool chains. In terms of supporting libraries, we also work with the maths libraries guys, OpenBLAS, FFTW, and also from Silicon Partners, their libraries, Cray, LibSci, to get their libraries optimized for ARM architectures. We also work with the communities to try to get any development to the open source area possible. I've got 3 colleagues who sit with the Fortran Standards Committee, so we're very active there. We also work with the US National Labs and other companies like IBM, NVIDIA, in terms of the development of the Fortran Compiler through the LLVM project. And we, as I say, over 70% of the work, the development work in ARM is for GCC. So you can see we do actively support the open source community. We also have a community website where we encourage anyone to contribute to, and what this does is it lists packages and how to build them with our compilers or open source compilers. And if you want to, if you're on an ARM architecture and you want to, you have a package you want to build, I'd recommend looking here first, because you might find information on how to build it. If not, you're very welcome to add your own package if you building your own. We encourage contribution to this site. Just as a general overview, we have lots of well-known CFD, molecular dynamics, infrastructure applications, all working on ARM, no problems. The well-known HPC benchmarks have all been tested, and there are mini apps as well if you want to look. But in general, if it works on any other HPC architecture, it should work on an ARM HPC architecture just as well. We also encourage membership of the ARM HPC user group, AHUG, and there's a groups.io mailing list that you can sign up to get information on that if you're interested. There's also the commercial, on our commercial webpage, developer.arm.com, which has a lot of links, not just to commercial, yeah, not just like commercial offerings, but also, you know, links to open source or how to get your application built. And we also run lots of hackathons throughout the year. So we usually have events at SC. Last time we had a very well attended event, over 50 attendees for a hackathon on SVE. For that, the attendees were able to access Isambard 2 with the 864FX processors. So for the next part of the talk, I'll cover actual compilers and libraries and tools and how you can use those. I won't go into too much detail, but I can do that at the end if needed. So as I've mentioned, we do contribute quite significantly to the GNU toolchain, and this might surprise some because you know, as a commercial company, you wouldn't perhaps consider that we do spend a lot of time getting code sent to GNU, and we do this obviously because we work with, you know, the mobile phone sector and others who are heavy users of the GNU toolchain. So in terms of what GCC offers for ARM, well, it's quite a lot. GCC 10.2, which is the current GCC, it does have a lot of optimizations available for ARM-based architectures. You can see that there was work recently added for SVE. You can use ARM C language extension type intrinsics, which I'll talk more about tomorrow. If you want to use intrinsics to build your code with, that's all supported with GCC 10.2. They've done work as well to improve vectorization for SVE. You know, things like accessing data, and also the cost model for doing the vectorization. That's quite well developed now. And as I mentioned, the ARM C language extension intrinsics, you have support there for recent ARM instruction set architecture additions, notably, you know, transactional memory extension. What this does is it improves the thread level parallelism of your code. So if you're using threads on an ARM-based architecture, the TME could help. And also the matrix multiply extension, that adds support for things like general matrix type multiplication and operations, maths operations. And as we've also mentioned, you know, half precision support is also there with GCC 10.2. There is also support for SVE2, which is what's coming after SVE. So SVE2, I'll mention more on another time, but that's an extension to SVE with support for like digital signal processing and kind of multimedia type applications. So maybe not so relevant for HPC, but I'll mention it anyway. But yeah, there is a lot of support in GCC 10.2 for ARM-based architectures, and even more coming in GCC 11. So the actual CPU of the A64FX is supported in GCC 11. So certainly a compiler to consider when using ARM-based HPC architecture. I should also say as well, while we're talking about GCC, we also contribute heavily to the LLVM community, as I mentioned. I mean, currently, if you were to use the ARM compiler, it's based on LLVM 9. And the next release of the compiler will be based on LLVM 11. In terms of maths library support, all the well-known libraries that you choose are, they work on ARM-based HPC, just like any other architecture. The GNU libraries, the more sparse-based solver libraries, we all contribute to their development, so that they're available if you want to try them. In terms of commercial offerings, so we have what we call the ARM Linear Studio. Now, this is a bit of a confusing title because it covers compilers, maths libraries, and basically profiling and debugging. So you get quite, if you look at ARM Linear Studio as a whole, you get quite a lot of tools. So I'll cover those in some detail for the rest of the talk. This slide really just describes what ARM Linear Studio is in another diagram. In terms of compiler, we talk about the ARM compiler for Linux, and what this includes is a C++ compiler and Fortran compiler, together with the ARM performance libraries. Now, the ARM performance libraries are the libraries like BLAS, LAPACK, FFTW, your optimized maths libraries. Whereas ARMForge is the DUG application, profiling application. And I should also just say as well, ARMForge is cross-platform, so it doesn't just run on ARM-based HPC architectures. You may also be familiar with ARMForge running on x86, whereas the ARM compiler is only for ARM architectures. So in more detail about the ARM compiler for Linux. So the ARM compilers, the commercial compilers, in terms of the C++ compiler, it's based on a LLVM Clang front end. So if you're familiar with that, this should be quite well known. It's fairly up to date with recent C++ developments. It has good auto-vectorization for both the scalable vector extension architecture and Neon as well. And it's got support for OpenMP 4.5. In terms of the Fortran compiler, it's based on a Flang front end. So Flang was an open source project from PGI a few years back. We took that and worked with the open source developers there. We also added, we've done a lot of work in terms of bug fixes and optimizations for our architectures in that. And just like the C++ compiler, it's got good auto vectorization for our vector extensions. Fairly good OpenMP support. We are hoping to move to a new front end over the coming years based on the F18 open source project. One reason for this is that project is based on code written in C++, so it's a lot easier for the compiler developer to work with. Excuse me. And it has better support for OpenMP 4.5. But that basically summarizes where we are currently with the open source compilers. Sorry, the commercial compilers. In terms of the maths libraries that we provide on the commercial side, we have the ARM performance libraries. Now, what these are basically routines which take the current laypack and they're optimized for ARM architectures. So what that means is that they have been hand tuned for for ARM. So they're aware of things like microarchitectural features in some cases, but generally they're hand optimized, so they should give best in class performance. Obviously that's not always the case for every single routine, because there's a lot of routines, and sometimes an open source library might win if it's had extra development where these are missed. Or the other way around, but generally we aim to give the best performance with these libraries. And I mean, basically you can take a variant of this for whichever particular architecture you're using. So if you're using a processor based on the ARM Neoverse N1, then you would take that variant of this library. And they're very easy to use. I mean, they're just a library. So you just link them against your code, and the executable should then bring in these optimized versions. So in terms of performance, I mean, this graph for DGEM gives you a general idea. In terms of the number of threads, as we increase the number of threads, the efficiency is good, and you can get close to peak performance with these routines. Recently, we've added more support for sparse matrix vector and sparse matrix multiplications, and notably, these routines are available for both GCC and ARM compiler for Linux. So you don't have to have the ARM compiler to use these. You can use GCC. You can build your own GCC and link these libraries against just the same. As well as the ARM performance libraries, there are vendor-provided maths libraries also available. As I've mentioned, we've got HPE, Craze, LibSci, Scientific Library. They have optimized math routines for ARM architectures, especially, on Isambard 2. They're all available. Fujitsu has its own optimized math library, SSL2. And NVIDIA as well. They have a software development toolkit which has very good support, both in terms of compilers and maths libraries and other tools. So finally, just to summarize, for what other commercial tools we offer. So ArmForge consists of a debugger known as DDT and a profiler called MAP. Now, DDT is essentially based on GNU GDB, the debugger, but it allows you to debug your code at scale, and there's much more functionality. It has a nice GUI that you can use. You can try to debug at scale, so you don't need to scale back your problem. If you're using lots of MPI tasks or something like that, or lots of OpenMP threads, it allows you to look at the source code. So if you have something like a segmentation fault, and you have a problem with memory, you can then interrogate memory. You can look at Fortran arrays, or you can use C++ style malloc interrogation. You can also get down to the assembly if you want to debug at assembly level. And it recently has the capability to debug Python interpreted source. So what this means is that you can actually get back to the line of source in your Python code that caused the bug or problem to happen. So it's a very powerful debugger. The other component of ArmForge is the map profiler. So what the profiler enables you to do is to find bottlenecks, hotspots in your application. Again, map is very, very easy to use. You can basically just put map in front of your application when you launch it, and map will launch the application and then profile it for you. But there are other ways of using map. It's a very powerful tool. It's a sampling based profiler, so it's not a tracing type profiler, and it gives you a good overall idea of how your code application is performing. There are a lot of there's a lot of functionality that you can use with it. It's got good support for performance metric interrogation, so for performance counters on ARM architectures, you can look at those. Recently, we've added a new feature called Statistical Profiling extension that enables you to look at performance of certain counters on ARM. And we're currently at release number 21, which was released yesterday. So if you want to look at that, it's just out. To give an idea what it looks like, so DDT, debugger, you can run it with this nice GUI. You can see that you can look at your source code, you can look at memory usage, you can get a breakdown of memory usage, you can track any memory leaks, you can look at MPI performance if there are any deadlocks or problems with hanging tasks, then you can interrogate them with this GUI. But you don't have to use it as a GUI. You can use it offline if you want, or you can use it as a separate laptop machine-based client, so you can do your debugging and then look at the output on your laptop. Similarly with map, the profiler, that offers a similar GUI that gives you a nice breakdown of your application performance. You can look at how the overall runtime breaks down in terms of say IO, MPI performance, thread performance, how the CPU is performing. Are you achieving peak CPU performance? Are there any memory leaks? And again, you can get back to your source code and interrogate where you're at. You can also look at the You can look at the thread, sorry, the current stack. You can do a stack backtrace, and you know, there are some really powerful ways you can use map as well. You can even define your own metric for interrogation. So if you have a CPU metric, or for whatever performance counters are available with perf or something, then you can define your own. If you want to look at maybe level 1 cache usage or TLB buffer usage, you can define your own metrics. But there are predefined metrics already available if you don't want to go that route. And finally, in terms of vendor provided libraries and tools, you know, NVIDIA provide a comprehensive, you know, they have comprehensive toolkit that includes their Nsight profiler. They've got, you know, debuggers. Similarly, Fujitsu, they have their own debugger and profiler. They have a profiler called the Fujitsu Advanced Performance Profiler, which has a very good GUI. And it's all very powerful. Cray, HPE have their own perf tools. So you've got CrayPat and Cray's debugger to use on ARM architecture, just like any other architecture. So there's very wide support. That really covers the talk, but I haven't really gone into any depth about what compiler flags you might use or things like that. So if you want to discuss those, please ask. So thanks very much.
Thanks, Phil. Participants, feel free to ask questions. Please unmute yourself, introduce yourself, and ask questions.
Hi, Phil. This is Amit Mankodi, and I'm currently working on a little bit of research area in the performance modeling area. I usually do measurement of performance and power on the x86 based machine using some libraries. I was trying to find something similar to do on the ARM-based platform. So can you suggest any good libraries where I can measure power on generally major types of ARM-based platforms?
So basically, you want to measure power consumption, is that right?
Yeah, power consumption for the application while it is running. So basically, I want to know how much power is consumed when the application was actually running.
Okay, it's a good question because our processors are you know, fabricated by different vendors. Then it's processor specific, really. I mean, are you using a current ARM-based system, or do you have one in mind?
I'm using the ARM-based boards, usually the mobile development boards, which are available, and we have formed the clusters out of it. So I'm interested in basically knowing what is the power consumption for the MPI-based application, which I run on the cluster. In order to measure that, I cannot actually measure the power consumption on each board. So for the cluster that we would build in, let's say, x86-based system, we could use tools like Hpe, which allows us to measure the power for the cluster. You know, we can measure for individual machine and then do that. But for the ARM, I was not able to really find any specific tool that would allow me to do it.
Have you managed to find any counters that might be available on the system that you're using?
So the PAPI tool actually uses the, I guess, the RAPL library for the Intel-based systems, which is what I was using with PAPI. But for ARM, I don't know if it is able to collect some performance counters data to measure the power consumption.
All I can say is it's possible, but
okay,
you'd have to look in more detail because it depends. It depends what OS you're running as well. So you'd have to make sure that the correct that the OS that you have is exposing the right counters. You'd have to look at what counters. There should be some counters available for the architecture that you've got, because you'd expect, you know, those to be in the design that are measuring some kind of power. But whether or not the OS exposes those is another question.
Okay, so we are using Linaro, as you mentioned during your talk. So we are using Linaro OS for that.
Yeah. So
I'll check on that. Thank you so much.
Yeah, no, thanks very much for asking. It is a good question, because we are getting questions like that. Because we have for the Marvell Thunder X2, there's a project ongoing at the moment where they're trying to do, just as you said, you know, measure the power for that processor. But Marvell have actually written an application that does this. But even so, if you want to look at it in more detail, you've got to check that the OS is you know, making the correct counters visible in user space.
Correct.
You know, rather than just kernel space or something like that. You know, because that can happen sometimes. But yeah, it's an interesting question.
Thank you.
Hello, I'm Dinesh Rao from Manipal. Okay, so suppose a client asks for 2 cores. Can you merge the 2 cores and give one single unit out there? Because the space taken may be 1.5 times if you merge the 2 cores. Maybe power consumption also could get reduced.
Well, again, it would depend on what architecture you have. In general, are you talking about using 2 cores as, I mean, do you mean physical cores or
IP, you are having one IP for 1 core. Suppose a customer asks you to give 2 cores. Can you merge the 2 cores into a single one so that the space occupied by the IP is less, power consumption is less? So 64 cores, instead of that, maybe you take space for 32 cores or 40 cores.
Well, in terms of cores, are we talking about an ARM core or a core on an ARM designed CPU?
Yes.
In general, I think if I understand the question correctly, I think it's possible.
Okay. The other way around, say your client asks for a few cores and they have IPs for memory, cache, etc. They integrate it together, right? So suppose they give you the memory, cache, etc. and ask you to build a processor. Would it be more efficient?
Right. I understand the question a bit more now. So yeah, I mean, the way we come up, so the partner can choose either a core or architectural license. Now, if they choose the core license, that core will have been designed based on input from, you know, colleagues who have worked with the community, so say the HPC community. So the HPC community might think that having 2 256-bit wide vectors per core is a good idea at that point. So that will be the design for that core model. And if a partner then wants to take that at the time and then design their own chip, they could they would have more limited scope for incorporating any changes for their design. But on the other hand, if they went from the beginning with an architectural license, then they could add as many cores or as few cores as possible on a for a chip. There's more freedom on that front. If that kind of answers.
Anyway, I'll go to the software side. One, are there any hidden instructions in ARM so that because you are using a commercial version of the compilers, right? So do those compilers use any hidden instruction so that the performance is better? Because code is anyway in the open source community, right? Code for any optimal function will be there in the open source community. How do you get better libraries? Is it through any hidden instructions around, which is not open to the public?
No, that's a good question. And the way it works is that we work with the open source communities. So, both GCC and LLVM. Now, we like to upstream anything, any knowledge that we find back to those communities. What can happen is that this can take time. So it might be that if you see the commercial compiler may have the developments before the open source, more than likely it will have the developments before the open source variant. But this doesn't always work. It doesn't always work that way because, for example, on the A64FX recently, I've been working with the GCC compiler as the main compiler because for the application that I've been using, it gave best results. So I could build my own GCC. I didn't need to use the commercial compiler. It's just you just take whatever works best with your particular workload or application. And it's not just the compilers. It's also the maths libraries as well. It might be that depending on what maths routine you're using, your application's using, there could be an open source variant that somebody's hand tuned for a particular ARM architecture. And it might work best that way. So I guess, in general, it's best to just try the range that are available. It's certainly not the case where you can recommend one particular compiler as the best option, if that makes sense.
Okay, thank you, Phil. That's all from my side.
Thanks.
Anybody else wants to ask any question? We have time for probably one more question.
Hello.
Hi.
Yeah, this is Manjunath from CDAP Pune. So my basic question is that is there any benchmark results related to MD codes like LAMPS, GROMACS, or Quantum Expresso on Fugaku-based ARM architecture?
There are a few publications that are available from Bristol that do they do show performance for I think LAMPS is one of those applications, but certainly applications like LAMPS, so you can get a general idea. Yes. If you want to email me, I can get you the links.
So can you share our links?
I'll have to find them, but yeah.
So our preliminary experiment with respect to this Fugaku ARM architecture, we are not getting the better performance compared to the Intel-based Skylake architecture. So we wanted to have some idea on comparison of both architectures. So if you send some link and material, it will be great helpful for us.
Okay. Just out of interest, have you you said you've tried the Bristol-based architecture? Is that right? Or you've tried the Bristol-based Isambard architecture? Is that correct?
Mr. Manjunatha, you are muted.
Yeah. So can you repeat the question?
Phil is asking if you have tried the Bristol-based architecture already. Okay.
Hello?
Any other
So,
just quick? Yeah.
yeah. So I'm not getting the question. So exactly what he's asking me.
I'm just checking the results. Actually, we haven't got. I don't think we've got results for lamps.
Okay, lamps.
I'll double check. But yeah, I'm just checking now. So no, there. Yeah, so no lamps. I'm sorry about that. But if it's of interest, we can certainly look into it.
Yeah. So basic our observation is that MD code is not performing better on the Fugaku ARM architecture compared to this one. So, but when we tried for a CFT code like OpenFOAM, it is not that much bad with respect to the MD code, but it is better than that. So, if you have anything related other than lamps, any MD code will be useful for us. Thank you.
Okay. Yeah. Thanks. Thanks very much.
All right. Thanks a lot, Phil, for your time and for the nice presentations. And I'm also thankful to all the participants for attending this talk. Tomorrow we'll meet at 3 o'clock IST. Again, we will be talking about the ARM ISA as well as the AIML with ARM HPC. Thank you very much. See you tomorrow.
Thank you very much, everyone. See you tomorrow. Bye.
Bye, Phil.
Thank you, Phil.